Hi everyone, welcome back. So let's continue our series on nuclear energy. This time we're focusing on nuclear processes, and the big concepts we'll be getting into in this next playlist is one, just how do we determine if a nuclear reaction is allowed? When I say nuclear reaction, think chemical reaction. And the second is, what is this thing called a cross-section, which helps me determine how likely that reaction is to happen? Let's jump right into it. So there's certain rules that are going to control what nuclear processes can happen. But the first rule is that you actually have to have something collide to start it. We have to have two particles. Could be a neutron in a nucleus, could be a proton in some nucleus, it could be two protons, two neutrons, whatever. They have to actually ram into each other, they have to hit before the reaction can start. Now, chemistry is complex. If you take in chemistry or organic chemistry, you realize that. Because there's 118 different elements, at least, that we can usually have, and we can combine them in countless ways. Now, nuclear chemistry is, sadly to say, even more complex. Why? Because we have 2,000 known isotopes. And since I have 2,000 known isotopes, it means there's even more ways we can combine them. Which sounds terrifying, but we don't use every single isotope. But when you're like in the Large Hadron Collider or something, you have to deal with a whole lot more than just the isotopes. You're going down to quarks and all these other kind of particles as well. But let's figure out how we can determine which of these reactions between these isotopes are actually possible. Well, here we go. All nuclear reactions can be written in the following form. As a note, the lowercase is simply saying that's the small thing on either side. The uppercase is saying that's the big thing on either side. And so I have a small thing plus a big thing equals a big thing plus a small thing. You don't have to have one small thing, you don't have to have one big thing. You can have two small things. It can work out either way. And so each of these laws has to follow, each of these reactions has to follow four governing laws. First off, the number of nucleons, that's the number of protons and neutrons, that can't change. I had two protons and two neutrons to start. Well, at the end, I'm going to have that same number total. I might have more protons, I might have more neutrons. Things can change within reason. So the second law says how much they can change. So in the first case, maybe my bigger particle had two protons, this one had one. In the second case, maybe my smaller particle has two protons, and this one has one. It can switch. That's allowed. Or it can combine so one has three and the other one has zero. Beyond that, which we'll get into later, is conservation of momentum and conservation of total energy, which tells us what direction are they going and how fast are they going after these reactions and after these collisions. And also, how much energy are they holding? Okay, so the transmutation of elements. When you think of transmutation, you might be picturing an anime called Fullmetal Alchemist, or some alchemist in a video game who's trying to turn lead into gold. Well, the thing is, we can change one element into a different element. And this is achieved by Rutherford in 1919. So what did he do? Well, he had nitrogen. It was a bunch of nitrogen gas, and he bombarded it with a stream of alpha particles. That's a fully ionized helium nucleus, which you can see right here. What happened is after that helium collided with the nitrogen, it turned the nitrogen into oxygen. So it gave it one of its protons. As well as one of its neutrons. And a hydrogen shot off from that. So it lost the protons from being helium to hydrogen. Now the cool thing about this was he was able to tell that this happened because he had a screen which was very, very sensitive to oxygen. It would give off flashes of light whenever oxygen hit it. So if he has only nitrogen gas here, no oxygen, it won't give off any light. But when he sends that stream of particles into there, it did give off light. So he knew that he was actually causing the nitrogen to change into oxygen through these collisions. So let's try this out. Let's see if this experiment here actually followed our conservation laws. So we'll write it out in our earlier form. So small thing, helium, plus big thing, nitrogen, is equal to big thing, oxygen, plus small thing, proton, hydrogen. Okay, so we have two laws we're going to be checking, which is conservation of charge and conservation of nucleons. And so first off, conservation of nucleons. That's the top number. So 4 plus 14 has to be equal to 17 plus 1. If it's not, then this equation can't happen. but it does equal. 14 plus 4 is 18, 17 plus 1 is 18, it checks out. Conservation of charge, that's the bottom number. Helium has 2 protons, nitrogen has 7. Oxygen has 8 protons, hydrogen has 1. So 8 plus 1 is equal to 9. 2 plus 7 is also equal to 9. This equation works. This is a reaction that can actually happen. So these are the two easiest conservation equations we deal with. Momentum and energy, they're a little bit harder, but these are where it starts. If these don't match up, then the equation you're writing down, the reaction you're writing down can't actually happen. Or there's something else going on and you've broken the laws of physics, which would be really cool. So we'll stop here for the day. Thank you all so much, and I'll see you all next time as we continue through this section on nuclear reactions. Have a good one. Bye-bye.